Okay, so welcome back. Tomorrow is your big exam. I hope you've been studying and I hope this helps. This is 2017. I don't remember what month, but this is 2017 right here. See? Okay, so the question asks, an experiment in which a magnet is allowed to fall through a coil was conducted to test the concept of induced EMF. The voltages were recorded at different time intervals, and table 1 shows the results. So you have time in milliseconds, and you have the induced EMF, which is the electromotive force, which has volts. Then the question says, using a scale of 2 centimeters to represent 5 milliseconds on the horizontal axis and 2 centimeters to represent 0.5 volts on the vertical axis, plot the graph of induced EMF volts versus time ms on the grid provided on page 5. So I printed out 2 test papers so you can see it done together. And so here they have, they said, first of all, we need to follow directions. It says, using a scale of 2 centimeters to represent 5 milliseconds on the horizontal axis, meaning going across here, we're going to use this. So this EMF is the y-axis. This is EMF versus time. So EMF will be on the y-axis, and then time will be on the x. So we're looking at our time, and the time is going 0, 5, 10, 15, 20, 25, 30, 35, 40, right? So it's going in 5s anyway. So we could go 0 from here. One of these is 1 centimeter, so 2 will make 2 centimeters. So we're going to go across. So we have 5, 10, 15, 20, 25, 30, 35, 40. Probably asking where I started here, and that's because we have negative numbers here. So we have to make space for the negative numbers. And it says on the x-axis, they want you to have 2 centimeters to represent 0.5 volts, every 0.5 volts on the vertical axis. So the vertical axis is the EMF. So we're going to label this one time in milliseconds, and this one is EMF, electromotive force in volts. So we're going to go here every 2. So remember, every 2 we have negative 0.5, negative 1.0, negative 1.5, negative 2.0. So this is good. And then we have now, we're going to go up again. This can be positive now. Negative 0.5, 1.0, 1.5, 2.0, 2.5. And our last positive point is 2.5. We could just got one more, 3.0. And now we could start plotting. And it says when it's 0, when the time is 0, the EMF is 0. So our first point will be here. Then when it's 5, when the time is 5, it's 0.25. So we know this is 0.25 here. And I showed you how to work this out already, but just for good measure, you want to figure out what this is in between here. You just say, oh, this minus the 0, because that's the 2 numbers. The big number minus the little number divided, and we just want to figure out what this is. So this is 2 spaces, 2 big spaces, divided by 2, 0.25, right? Then we know that at 10, it's positive 1. At 15, it's 2. At 20, it's 2.5. At 25, it's 1, so it comes down. At 30, it's negative 0.75. This will be 2.25, 5, negative 0.75. And then we have at 35, it's negative 2. And at 40, it's 1. Okay, so this is a nice sine wave. You can see here, and we could do that. So let's do that now. A nice sine wave. Yay. Then we're gonna draw our axis. Boom. And we draw this one here. And we give the graph a nice title, as usual. Okay. And we're good to go. We could write something like this. Graph showing electromotive force versus time in meters, in milliseconds, sorry. So that is our title right there. And that's that. That would give, this should give us 8 max, right? Once you follow the directions. So I hope you got a graph like this. Now if you turn it over, it says, use your graph to determine the induced EMF after 12.5 milliseconds. So after 12.5 milliseconds, you go back to your graph. And all you do is extrapolate. So you look over here, 12.5 milliseconds. So you look for 12. So we know each thing in here, this is 16, 17, 18, 19. So it's every 2 is 1. So it's 11, 12. This is 13. So this is 12, 13. So this is 12.5. You scroll up. And that we do, we just go across here. You can use your ruler to make it easier. And you put your arrow, your dotted line. Okay. And so this, you want to figure out what each of these are. And this is how you do it. Again, you would say 2.0 minus 1.5. That's 0.5 divided by how many spaces in here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it's 10. So each of these is what? 0.05. This is 1.55. You add 0.05. This is 1.55. 1.55 volts. And then it says the time in milliseconds other than at the beginning of the experiment when the induced EMF was 0 volts. So other than this, when was it 0 again? It was right here. Because this, when x has a value, y is 0. So here, and now we say this is 26. 27, so about 27 milliseconds. So that would be that one. Okay. Then it says Kevin A physics student conducted an experiment to determine the effects of electromagnetic induction. He used the following apparatus: coil made up of fine wires, a sensitive galvanometer connecting wires, and a bar magnet. Figure 1 shows the setup of the apparatus used by Kevin. So we have the bar magnet, the coil, and all that. Now, the magnet was pushed into the coil with the north pole entering first. Draw on figure 1 the direction of the induced current and the direction of the arrow of the on the galvanometer as a result of this motion. So whenever you're pushing north side of a magnet into a solenoid, this is a solenoid, the end that is facing the north magnet will behave so as to oppose the action. It's a conservation of energy. So this becomes north, and because of that, you would use your right hand grip rule. Okay, so your right hand grip rule, and you would try to figure out, so your thumb always will be in the position in the direction of the north, and this is north right here. However, the coils are coiled a bit funny, so what I would do is turn the paper around, because they're coiling it this way, here, here, here. So I turn it this way, and then I would open up my hands like this to wrap my hand around the coil this way, right? So I would wrap my hand around the coil this way to figure out the direction of the current, right? And so I turn my hand this way because remember, north is always in the direction of your thumb. So I wrapped it around, and so therefore we will be going down and then up this way. So I'm going to do it all down from the back. Right? And when I turn it back around this way, it'll be going up. So come around here, this way, and the galvanometer will go that way, and then this way, up, and then down, right. So you see it here. Good. Good. So that's the direction that it would take. And remember, your thumb is always in the position of the north. So you could put your hand like this once it's like this, or if the north is over here, you put your hand like that. Okay? Explain why an induced current is produced. That's because the magnetic field lines are being cut constantly. Why is it necessary to use a sensitive galvanometer? Why do you think? Well, output. The changes are small. And hard to detect. So a sensitive instrument is key. Next question. The magnet is then pulled out of the coil, shown figure to the direction of the induced current as a result of the motion. So once you're pulling it out, this is going to behave to oppose this action, because now it wants the magnet to stay in there. So now this is the south pole. This is now a south pole. And so because this is the south pole, the north is over here, so it's going to go in a different direction, right? It's going to go in a different direction. So whereas this was going up, it will now be going down, 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 down. And so this would turn in a different direction, going that way, up, Right? So we just go opposite. Now, state 3 changes are adjustments that Kevin could make in this experiment to increase the induced EMF. So 3 things. You need a stronger magnet. You could make more coils in the solenoid. And you could increase the speed at which you're pushing the magnet in and out of the solenoid. Then it says, describe what will happen if the magnet remains stationary in the coil, because it won't be cutting the magnetic field lines anymore. No current will flow. Alright, so figure 3 shows a simple layout of an AC generator. So once you see this word here, generator, that means you're using your right hand, using Fleming's. I think it's 1M. Fleming's right hand rule. And you have to have your hand like this. So this must be 90 degrees to your second finger, and the second finger must be 90 degrees to your third finger. Okay? And this represents motion, this represents the direction of the magnetic field. So it always goes from north to south, and this is the direction of the current. Now it already tells us that the coil is going to turn down. So we put it down. No, you can't even see, but if you put it down, remember this is the motion, so down will be the thumb going down. This must go from north to south, so I must point this finger going from the northern direction to the southern direction. So imagine my hand is like this, and I just flip it over like this. So I flip it like that, twist my hand like that, and you know that this is the thumb underneath here, going down, that's the picture right there, and this is the finger for the field going across, and so the current in this side of the wire is coming towards me. Okay, so that's the direction of the current right there. It says draw on figure 3 the direction of the induced current if the coil rotates in a clockwise direction. Now, if the period of rotation of the coil is 0.02 seconds, calculate its frequency. We can use this nifty equation where frequency is equal to 1 divided by the period. And so 1 divided by 0.02 seconds will give us 1 divided by 0.02 will give us 50 hertz per second, equal to 50 hertz. And then it says here, if the speed and direction of rotation of the coil are constant, sketch a graph of voltage against time to show the output for the generator for one complete cycle. So it says for one complete cycle, given that it starts rotating from its current position. So one complete cycle includes a crest and a trough. So that's that. Okay? So this represents time, and this will be the EMF right here. Yes, it says one complete cycle. Let's see if any more. Oh, and that ends the first question for 25 max. Hope this helped. I must say, hope this helps. So you should have your sine wave, and look at this. The answer that they asked for the last question is what you generated in the first question. You just didn't complete the cycle. And then remember, you have to learn to extrapolate properly. I would have shown that in a couple of videos. So look through all my videos and you'll find that. So these are all extrapolations. So they're basically just testing your math knowledge at this point. This one, remember to use the right hand grip rule. Please look in your concise text. They have a very, very good explanation for it. All right. This as well is in your concise text. So is this is in your concise text. All of this is in your concise text. So please, please, please go back to that. All is not lost. I hope you got the same answers I did. See you around for question number 2.